Alright, so this is card 114. And we are going to start talking about circles. Alright. So, I'm going to write two. Well, let's just start off with the theorems right away. In a circle, a radius perpendicular to a chord bisects the chord. A radius perpendicular to a chord bisects the chord. Okay? Then we have in a circle, a radius that bisects a chord is perpendicular to the chord. So it kind of says the same thing but backwards. Okay. And then we have one more for this type of theorem, and it says in a circle, the perpendicular bisector of a chord passes through the center of the circle. Alright, so let's see a picture of what these three theorems look like. And it's a pretty simple picture. Gotta get my compass out. Alright, so what we have first is a circle. I'm just going to make like a 1-inch radius circle. It doesn't matter though, okay? So here we go. Don't make it too small or too big, that's all. Alright. That's why I typically don't go back over the same thing I already went over because that happens sometimes, but not a big deal. So, in a circle. And let's say center is like right here. Right? And we have a radius. Okay. And we have a chord that's perpendicular to the radius. So what these, and let's say this is A, B, let's say this is D, and usually the center of a circle they say is O. Now, if this radius is perpendicular to this chord, then bisects the chord. That's essentially what this theorem says. Okay? And that's pretty much the only picture that you would need because it covers all three parts of that theorem. Alright? Let's look at the next card, 115. In a circle, comma, or congruent circles. Congruent, so comma. Congruent chords are equidistant from the center. And the converse is also true, which would be in a circle or congruent circles, chords equidistant from the center are congruent. All right, let's draw a picture for this one. I'm going to use the same radius because that one made a good sized circle. Okay. So there's my center. And what I would have here would be, say like I have a chord over here. Doesn't matter exactly where we draw it. I'm just going to make mine about 1.5 inches long because I want to make it the same length on this side also. So we have two chords, and the theorem says that if they're equidistant from the center of the circle, and that's the perpendicular distance, right? So let's label this CD and AB. And so this distance is the same as this distance. So if they're the same distance from the center of the circle, then the two chords are congruent. Alright, so let's just write segment CD or chord CD is congruent to chord A, B. And that's the picture for that one. Alright. Let's go to 116. Okay. In a circle or congruent circles, congruent chords have congruent arcs. Then we can do the converse also. In a circle or congruent circles, congruent arcs have congruent chords. Okay, so let's draw a picture of that one. Ooh, that one did not come out too good. Alright. So, let me just double check this one. Yeah, congruent arcs. So, we're going to do the same type of thing we did before. We're going to draw two chords. This time I'm going to make them 1 3/4 inches. So, What this theorem says is, well, let me label my points first. O, C, D, A, B. If these chords are congruent, then the arcs that they intercept are also congruent. All right? So CD, segment CD, congruent to segment AB, and arc CD. Now remember how we draw the symbol for arc? Looks like that. Arc CD then is congruent to arc AB. Okay? Next card, 117. In a circle, parallel chords intercept congruent arcs. So let's say we have two chords that are basically parallel. All right, let's say this is AB, CD. So if AB is parallel to CD, then we know arc AC is congruent to arc BD. Okay? That's what that says. That was 117. We're on 118. Okay. If a line is tangent to a circle, comma, it is perpendicular to the radius drawn to the point of tangency. Okay, let's see what this theorem looks like. All right. So here's our tangent touching the circle at one point. All right. So let's draw this as let's say this is A, B, D, and O. So if this is a tangent and this is a radius, then this is perpendicular. They are perpendicular to each other. Okay? So what we want to write is if line AB is a tangent and D is a point of tangency, then segment OD is perpendicular to segment AB. Okay? Now let's do 119. It says tangent segments to a circle from the same external point Alright, where were we? Tangent segments to a circle from the same external point are congruent. Alright, let's see what that looks like. Okay, so if we have tangents from the same external point, say that point right there. Alright, so say this is A, this is C, and this is B, and the center of our circle is O. Here we have two tangent lines from the same point, from the same external point. And whenever that happens, these two tangent lines are congruent. Alright, so let's see. If AB is a tangent to circle O at A, so if segment AB is a tangent to circle O at A, and segment BC is a tangent to circle O at C, then segment AB is congruent to segment CB. Then the two tangents are congruent. Let's go to 120. Okay, let's see what we got next. Common tangents are lines or segments that are tangent to more than one circle Alright, so common tangents are lines or segments that are tangent to more than one circle at the same time. Let's see. There's really two that we have to know. Okay? So let's try to draw this. Well, let's split this in half first. Alright, so Alright, so the first situation is where we have two circles, right, that are separate. So this is a situation of four common tangents, right? And that's for two completely separate circles. Alright? And let's draw in those tangents. Okay? And there are your four tangents. That's 1, 2, 3, and 4. Alright? And then we also, the other one that you have to know is 3 common tangents. And that's when you have, let me just see how they word it in the standards here. Okay, so this is for 2 tangent circles. And here's what this looks like. Alright, so in this situation, you have three common tangents. There's one that would be right. See how these circles meet at one point? Well, one of the common tangents would meet at that same point. So they're all touching at one point here. And then you could have one tangent like this, and one like this. Okay, so those are the two situations about common tangents that you need to know. There are other situations, but you don't need to know them. Okay. So we're on card 121 now. If two chords intersect in a circle, the product of the lengths of the segments of one chord equal the product of the segments of the other. Okay, and this is called the intersecting chords rule, which can be abbreviated as segment piece times segment piece equals segment piece times segment piece. Okay, let's see what that looks like. Alright, so if we have two chords intersecting inside this circle, and it doesn't matter how they intersect at all, so I'm just going to draw two chords inside this circle that are intersecting. Alright, just like that. And let's say that this length is C, let's say that this length is B, let's say this length is A, and this length is D. Okay? So our rule says that A times C equals B times D. That's it. Alright, let's go to the next one. Card 122. If two secant segments are drawn to a circle, from the same external point, the product of the length of one secant segment and its external part is equal to the product of the length of the other secant segment and its external part. So this is what we call the secant-secant rule. And what we would write for this would be the whole secant times the external part equals the whole secant times the external part. Alright, so actually now that I'm thinking about it, maybe we want to, you're going to hate me right now, but go back one card and get rid of that. Because really, if we want to make it easier to remember, we should put it on one line. So segment piece times segment piece equals, it just looks much better this way, and it's going to be much easier for you to remember it this way. Okay? And then when we do this one over, we're going to do the same thing. Alright, so the whole secant times the external part equals the whole secant times the external part. And here's what a picture of this looks like. Okay. So we got a circle. We'll draw it from this side. Okay. Okay. So here's what we do. We have these two secants that are coming from the same external point. Okay, just like that. And this piece out here, we'll say it's A. And this piece right here, we'll say it's C. And then the whole length of this one, we'll call it B. And the whole length of this one, let's call it D. So if you have this, then A times B equals C times D. All right, and let's actually go back to this last card for a second. I just want to switch some of the letters because it's better just to make them all A times B equals C times D. So let's actually make this the C. We'll make this one the B. We'll make this one D. And that one will stay as A. So now we'll have AB equals CD. Okay, just to be consistent with our usage of our letters. Okay? Now we're on 123. All right. If a secant segment and tangent segment are drawn to a circle from the same external point, the product of the length of the secant segment and its external part equals the square of the length of the tangent segment. And this is what we call the secant tangent rule. This says that the whole secant times its external part equals the tangent squared. That's what this one says. So let's see a picture of it. Okay. So what we have here is we have a tangent to the circle, and we have a secant coming from that same external point. So it's a secant tangent. All right, now let's call this length of the tangent A. Let's call this length of the external part from here to here is B. And then let's say that the whole thing is C. Right? So then what happens is B times C equals A squared. All right? So that's 123. Let's look at 124 now. Let's see what's next. We're going to start talking about, let me see, angles and arcs now. Let's see. All right. A central, in a circle, or congruent circles, congruent central angles have congruent arcs. All right, now let's see a picture of what this looks like. What I do want to write on the next line though is central angle equals intercepted arc. And let's see what we mean by this. We have a circle and you have to remember now a central angle is an angle that goes from the center of the circle to the edge, like that. That is called a central angle. So if this angle is, say, 80 degrees, then this angle is also 80 degrees. Okay? So the measure of angle AOB equals the measure of arc AB. All right? So that's about it for central angles. Let's go now to an inscribed angle. Let's see. Okay, let's talk about inscribed. This would be card 125 now. In a circle, inscribed circles that intercept the same arc are congruent. the same arc are congruent. So it's important to remember that an inscribed angle equals 1/2 the intercepted arc. And here's how we draw this. Here's an example of an inscribed angle. An inscribed angle goes from one side of a circle to the other, like this. Okay? And you can see that it intercepts an arc, right? So if we were going to say this is B, and this is A, and this is C, if this is 100 degrees, then this angle is half of that, 50 degrees. So the measure of angle ABC equals 1/2 the measure of arc AC. All right? Now we'll do card 126. Let's see. This one is tangent chord angle equals 1/2 the intercepted arc. So we can go straight to a description of this one. If you have a circle, alright, and you have, now remember what this one said, it's a tangent chord angle, so that means what you have is a tangent and a chord. So first I'll draw a chord, right, and then you have also a tangent, like that. And you can see that it intercepts a certain arc, right? So if this angle right here is 60, then this arc is double that, 120. Or in other words, the angle is half of the arc. So the measure of angle, we have to label our thing here, A, B, C. Let's just make the center of our circle here O also. The measure of angle ABC equals 1/2 the measure of arc AB. Right? This angle is half of that arc that it eats. You can think of it as eating that arc. Okay? 127 we're on. Let's just see. All right. So the angle formed inside by two chords equals 1/2 the sum of the intercepted arcs. So let's see what this looks like. Okay, so here's how this works. Let's say this was 100 degrees and this arc over here was 80 degrees. These two angles in here would be 1/2 the sum of these two arcs. So each one of these angles would be 100 plus 80 is 180, divide that by 2. These would each be 90 degrees. Alright? So the measure of angle BEC is equal to 1/2 of the measure of arc BC plus the measure of arc AD. Okay? That's that one. So we're on 128. Let's see. Let's call this one angle formed outside of a circle by the intersection of two tangents. And the formula is going to be angle formed outside equals 1/2 the difference of the intercepted arcs. Let's see what that looks like. All right. So we have two tangents, right? Okay. Like that. Well, let's just label a few things. This is the center. We'll call this A, this B, and this C. So let's say this arc out here is 260 degrees, this big arc. And let's say this inner arc right here is 100 degrees. This angle is 1/2 the difference of those two arcs. So if you do 260 minus 100, you would get 160, and if you divide that by 2 or multiply it by 1/2, you would get 80 degrees. And that's what this rule says. So the measure of angle ABC equals 1/2 times the this is how you would write this, because they're both arc AC, right? But the bigger one is called the major arc and the smaller one is called the minor arc. So the measure of arc AC major minus the measure of arc AC minor. Okay? So that's it. I'm trying to think, should I fill in numbers for that? No, I think you get the point. That's 128. Okay. Now this is almost the same thing. Angle formed. Outside, by the way, this is card 129 now. Angle formed outside of a circle by the intersection of two secants. And it's the same formula, it just looks a little different. Angle formed outside equals 1/2 difference of intercepted arcs. Let's see it. This time we got two secants, right? So two secants. Okay. So let's say this is A, this is B, this is C, D, and E. Let's say this arc out here is 80 degrees, and let's say this little piece here is 20 degrees. 80 minus 20 is 60. Multiply that by a half or divide it by 2, and you get 30. So the measure of angle ACE, that angle right here, or BCD, doesn't matter, it's the same thing, is 1/2 the measure of arc AE minus the measure of arc BD. Alright? Then we have one more of these types, and it's card 130. So, angle formed outside of a circle by the intersection of a tangent and a secant. And once again, it's the same formula. It just looks a little different in the picture. The angle formed outside equals 1/2 the difference of the intercepted arcs. So let's see. Oh, it's going to put an O on this one, the middle. Alright, let's say this is A, and this is B, this is C, and this is D. And it's the same idea, alright? If we say that this arc is 100, and this arc is 30, 100 minus 30 is 70, and 70 times a half is 35. So the measure of angle A, B, D, or ABC is 1/2 of the measure of arc AD minus the measure of arc AC. Alright? Now, let's see what's next. So that was card 130. We got a little bit left. Let's see. Okay, let me just see. I thought we wrote this down already, but maybe we didn't. Actually, we did write that one, so we have one more to do with circles here. 131. In the same circle or congruent circles, congruent central angles have congruent chords. And the converse is also true. In the same circle or congruent circles, congruent chords have congruent central angles. Alright, so let's see what that looks like. Alright. If we have two central angles that are the same size, so say those two central angles are the same size, that means that the chords are the same. The chords that they form, right, are the same length. Okay? That's what that theorem says. And let me just go back to one card. So that's 131. Let's just go back to, let's see. Central angles have congruent arcs. Yeah, that's pretty obvious. Let me just see what we did here. Okay. Congratulations, you just made it through all of the circle stuff. So the next topic will be on transformations.